Okay, let's have a look at this concept called enthalpy. Enthalpy is a measure of the heat content of substances, and it's given the symbol H. Now, we can't actually measure the heat content of a substance, but what we can measure is a change in the heat content, and we define that as delta H. So a change in enthalpy, delta H, for a chemical reaction is defined always as the heat absorbed per mole of either reactant or product when this reaction occurs at a constant pressure. And we can put this algebraically as delta H, a change in heat content or enthalpy, is defined as the heat of the products minus the heat of the reactants. And once again, remember that it's the heat absorbed. That's why we put the products first. So we can get two things out of this. First of all, if the delta H value is positive, we're putting energy into the system, therefore our reaction will be endothermic. We're adding heat to it. On the other hand, if delta H is negative, so our reactants, or the heat for our reactants is higher than our products, we'll get a delta H that's negative. This will give us what's called an exothermic reaction. We're giving heat out, or the reaction is giving heat out into the environment. So let's look at this in more detail. On the left-hand side, we've graphically illustrated an endothermic reaction where we go from reactant to product. In this case, the H value, or the enthalpy value of our reactant, is lower than our product. So we have to put in some form of heat, we have to put in energy for this reaction to go from reactant to product. And this obviously gives us the heat of our products will be higher than the heat of our reactant. The difference between these two is our change in enthalpy, or delta H. And if we've added heat to the system, or energy to the system, our delta H value will be positive. On the other hand, if our heat of reactants is higher than our heat for products, our delta H value will be negative, because we subtract this one from this one and we get a negative value. So how does this play out in terms of chemical reactions? I have a chemical reaction here, and I've got it going one way, and I've also got the reverse direction. So our calcium oxide plus calcium dioxide gives us calcium carbonate, and our delta H value is minus 178 kilojoules per mole. Now, we already said if the delta H value is negative, we have an exothermic reaction. So this particular reaction will give heat out. It'll feel warm. If we reverse it and we break down the calcium carbonate to calcium oxide plus carbon dioxide, we find that our delta H value is reversed. So now we have an endothermic reaction. Now, another thing to note is we've got exactly the same value, either minus 178 for the exothermic or plus 178 for the endothermic. And this tells us that we have conservation of energy. Now, we also need to be very specific about what we're putting in our reaction. So I've got two examples up the top here. I've got one where we've got 2 moles of hydrogen plus 1 mole of oxygen to give us 2 moles of water in a liquid form. And we've got a delta H value of minus 572 kilojoules per mole of oxygen reacted. We've also got a second version where we've got 1 mole of hydrogen plus half a mole of oxygen gives us 1 mole of water. And we've got a delta H value of minus 286 kilojoules per mole of water formed. If we do a quick calculation, we find that this value is half of this value. So in going from 2 moles of water to 1 mole of water, we halve the value of the delta H value. And that once again tells us that our energy is conserved in the system as well. Also note that in this case, both of them are negative values, which we expect, because if we combine hydrogen with oxygen, we get an exothermic reaction. So that tells us we get conservation through the number of moles in the system. And the important part to take out of that is, are we specifying it as a reactant, or per mole of reactant, or per mole of product? The second, or 3 equations that I've got, give us something slightly different. So we have exactly the same reaction and product formed. The difference here is the form that our iodine is in. So the first reaction we've got a solid, the second reaction we've got a gas. And we get quite different delta H values for both of those reactions. In the first one, where we use the solid iodine, we get a value of plus 52 kilojoules per mole of iodine used. And in the second one, where we've used the gaseous form, we get a delta H value of minus 10 kilojoules per mole. Now, it turns out that the conversion between solid iodine to gaseous iodine is an endothermic process and requires 62 kilojoules per mole. Once again, if we subtract this value, being the smaller one, from this value, we get this value here. And that tells us once again that we have conservation of energy in this system. So if all we have as our products, our reactants are hydrogen gas and solid iodine, we can either add those two together and add heat to the system, or we can take our iodine and switch it to a gaseous form. Once again, we've got to put energy into the system and react this with our hydrogen gas here to form the same product, and it takes exactly the same amount of energy in both cases. So how can we use the information given to us by change in enthalpy? Well, obviously, if we perform a reaction and we can then convert it to per mole of reactant or product, our delta H value. We can also determine from our delta H value whether we have an exothermic or endothermic reaction, quite simply. And the next video that I'll do will be looking at some of those examples.